There are people connecting, so just waiting a little bit to start. Okay.
And then you can have it. So you probably don't need to use the funnel. Just make that sort of funnel shape thing.
Okay, we can start. Good afternoon to everybody and welcome to TMS today. The title of the seminar is Quantum Dots for Sensing and Switches Application, and it is presented by Ángel Campos Lendines. He is currently a PhD student at the Institute of Material Science of Barcelona. He received his bachelor degree in chemistry at the University of Jaén in 2015 and his master degree in science and technology of new materials at the University of Seville in 2017. After he worked as a researcher at the Institute of Material Science of Seville, fabricating thin film and nanostructures based on organic molecules for sensing application through high vacuum techniques. Currently, his research revolves around surface engineering, nanofabrication, and surface modification for new application in transistors as sensors and switches. So, Ángel, when you are ready, you can share your screen and start. The floor is yours.
I'm going to share my screen. I don't know if everyone can see my screen. Yes. Okay. Thank you, Sarah, for this nice introduction. As Sarah said, I'm working now at MAP in Barcelona, and I'm developing new applications for surfaces by engineering and surface modification by quantum dots, for example, for switches and sensing applications. This is the title of this speech. I'm sorry. Okay. I'm going to start with an introduction talking about what's a nanomaterial, fabrication of these nanomaterials, types. After that, we will move to quantum dots, talking about photoluminescence, factor affecting this effect, and quenching photoluminescence, which is so important for sensing application and switches. And I will finish this speech with some conclusions. Okay, first of all, it's necessary to define what is a nanomaterial. A nanomaterial based on the EU Commission and the ISO entity is a material which has one of their dimension below than 100 nanometers. They can, a nanomaterial is considered this kind of structure or bigger structure with containing nanomaterial inside. Finally, we need to get some structure in a nanoscale. So some example of that is, for example, nanoribbons, nanowires, sorry, thin films, nanoparticles, nanoonions, among others. This is a scale of the range of a nanoscale, and this you can see here it is in range of proteins, yeah, COVID, for example, also. And for a better understanding, I want to show you something. It's like if a person will be a sun, a real person will be about a nanoscale or approximately a nanoscale. So this is a very small range. For the fabrication of nanomaterials, there are mainly two routes. One of the routes is from bulk material, make fragments to obtain the nanoscale structures. Like, for example, in this gift, you can see a sculpture doing a sculpture from a bulk rock for getting a smaller one. The other way is from bottom up, using atoms, molecules, or others to make cluster, and after that acquire the nano structure. Like if you do a building with Lego pieces, for example, like in the video. So the main routes are top down and bottom up. And the classification of these nanomaterials are based in 4 different ways. For example, the most use is the most used is by their dimensionality, but also as it's more by their morphology, state, and chemical composition. By their dimensionality, we can find 4 different groups: 3D, 2, 1, and 0D materials. 3D material, for example, means that the 3 axes in the space are above of 100 nanometers, and 0, any of them are above 100, they are below. So some good properties of the nanomaterials are the small size, large surface area, quantum confinement, surface charge and stability, catalytic reactivity, and optical and magnetic properties. The quantum dots are in the group of 0-dimensional, as I commented, is because they are below than 100 nanometers of their axis are below. So moving to what is a quantum dot? A quantum dot is a semiconductor, a nanocrystal, which has a core, sometimes could get a shell, and always they have a ligands in order to avoid some aggregations. Some properties very interesting of this nanomaterial are the small size, like we commented, quantum confinement, discrete states, and photoluminescence. From the small size, this nanoparticle can obtain photoluminescence, but why? In the hypothetical situation in which we have a 3D nanomaterial, there is a band gap with a valence band here and conduction band. In the valence band, without any excitation, the electrons are moving here, and the effect of the increasing effect of the atoms in the bulk material creates an early continuous bands in the state, and it's like an approximation to a electronic cloud. However, this changes when we have a quantum dot, which we have a quantum confinement due to the small size and the small quantity of atoms. So the restrictive motion of the electrons are in discrete states, and after an excitation by light, for example, they move to the excitation band, and after the radiative relaxation, they will emit a photon, resulting in fluorescence. This is the effect of photoluminescence, excitation by a photon for emitting another one. Understanding this effect, we can see the properties of this kind of nanoparticles, which the most important properties to be controlled are the size, the impurities, defects, crystallinity, and ligands. Starting for the size, as I commented, is so important because it's a can create a quantum confinement which is necessary for the photoluminescence. When we are moving to a decreasing nanocrystal size, the band gap is increasing. This is this will affect to the fluorescence wavelength, the range of the emission of this kind of fluorescence due to at smaller band gap energy, we will move or we will approach to red spectrum. However, when the band gap is increasing, the energy is higher, and we will get a shift near to the blue or violet spectrum. This is very good property because based on the diameter of the nanoparticle, we can move or control the emission wavelength in different quantum dots. As you can see here, this is a real sample. Depending of the diameter, they will emit a different emission in the spectrum, in the visible spectrum. So impurities also can improve the photoluminescence. And here I want to show you an example, in my opinion, very good example. They tried to incorporate a manganese atom in different parts of the quantum dot, and in order to assess the quantum yield. Here it's inside the core, in the edge of the core and the shell, and in the middle of the shell. And you can see here how, depending of the position of the impurity, the quantum yield is improving. This is depending of you have a P or in donor depends, the quantum yield will be modified. This is a very good property. Also, defects is important to control because defects in the nanocrystal can promote a decreasing of the photoluminescence. Also, the multi-layers can promote the increasing of the defects, decreasing effect of these defects in the nanocrystals, resulting in a lower quantum yield. Crystallinity is it's another property to be controlled. Here is a quantum dot. It's a semiconductor with a mixture of different elements, and you can modulate the proportion of the atoms in this element. Of these elements in the nanoparticle. That promote change in the band gap. And as I commented before, the effect of the band gap is so important to see what is the wavelength emission of the quantum dot. So different crystallinity can affect to the band gap and create modulate the effect of the photoluminescence wavelength. So to finish this main properties to be controlled is the ligand. Ligand is probably one of the most important as to the size because they promote the the effect of avoid aggregations. But also they can reduce the photoluminescence depending of the type of ligands or the bonding, the ligand and the quantum dots, because there is normally ligands interact as a hole trapping. In a normal situation, we will have an excitation of the electron by a photon, and after relaxation, this quantum dot emits another photon with a lower energy. However, when we have ligands, this trap these electrons, avoiding the effect of the radiative recombination, resulting in a quenching of the fluorescence. Okay, with these properties, all of these properties can be used for sensing applications. Mainly exists two ways for determination of analytes or the use of quantum dots for sensing applications. First one's covalent bonding or not covalent bonding. When exists a covalent bonding, normally there is a ligand which interact with the analyte, or maybe the analyte interact directly with the quantum dot, but at the end there is a covalent interaction between the ligand and the analyte and the quantum dot in any way. For non-covalent bonding, but we can see, for example, electrostatic interaction, van der Waals force, among others. Normally, when we have an interaction between the analyte and the quantum dot, there is after the excitation, there is a electronic transfer from the quantum dot and the ligand. That means that the quantum dot will not get the normal with intensity due to a quenching for this electronic transfer. And we will have a low intensity in the fluorescence. Also, depending on the effect, this analyte can move the wavelength of the emission. In the opposite way, for example, in chemiluminescence, is the analyte which emits make an electronic transfer or Hall transfer from this analyte to the quantum dot, and we have the opposite effect. So I want to show you some examples with the most known strategies. In this example, they are using here a quantum dot with a tail, and by Fret effect, which is a fluorescence resonance energy transfer, there is a modulation of the wavelength due to the analyte they want to determine. But when you break the tail and the analyte has no any interaction with the quantum dot, the quantum dot receives or recover again the fluorescence. There are other strategies in which you have a tail, and after the phosphorylation, here, for example, an interaction with an analyte, again, we have the Fret effect, changes the emission. And another way is, for example, if you have different analytes or more than one single molecule or single analyte, you can also determine by the quenching of the fluorescence or the change of the wavelength emission. For example, they are also used as a pH sensors, which is very interesting because in this example, they are using peptide as a ligand, and a dopamine as a receptor or the medium for sensing the pH changes. And when the dopamine is reduced, we can observe here how there is not any electronic transfer from the quantum dot to the dopamine. So we have a good fluorescence here, the quantum dot fluoresces. And when we move to a basic media, the dopamine is oxidized. So there is an electron transfer from the quantum dot to the dopamine. in this case, there is a quenching, and we can control this quenching in order to know the pH in the media, thanks to the dopamine or electron transfer. It's another way. Another option, another example here is by chemiluminescence, as I commented before in the strategies. Here they want to determine the presence of radicals, and for example, these radicals can generate an electron injection or hole injection, increasing the fluorescence in the quantum dots. This is the opposite effect, but that I show you in the last samples. Here, I think this is a very interesting research because they can determine very accurate range the cancer cells present in an organism or body or whatever with cells. So they have quantum dots and they try to decorate with folic acid, affecting to the fluorescence by a quenching. After that, when this quantum dot gets inside of a cancer cell, there is a folate receptor, which is the author explained in this article, is a marker for cancer cells. This folate receptor removes the presence of folic acid on the surface of the quantum dot, resulting in fluorescence. So we can see fluorescence only in cancer cells. It's a schematic representation. In a normal cell, we will not see anything. However, in cancer cell, we can determine these kind of cells thanks to the fluorescence of the quantum dots. Other option could be for covalent bonding, for methyl sensing and recovery by covalent bonding or no covalent bonding. In this case, the quantum dots it's used, it's a functionalized with thiamine, which interacts with copper elements. And after the interaction, there's an electron transfer from the quantum dot to the copper, resulting in a quenching of the fluorescence. And after removing the copper, we can see how the fluorescence is recovered again. This is a covalent bonding strategy, but for no covalent bonding works perfectly well. In the case of in this sample, they want to determine iron in the media, and after interaction by no covalent bonding, there's an electron transfer from the quantum dot to the iron, because after remove this iron, we will recover again the fluorescence. As you can see, the strategy is always the same in many applications for sensing. Is based on the electronic transfer, or in one way or in the other way. And here, this is a new kind of sensor. It's very interesting, in which they are using a micro robot for motion analysis, for example, in order to discriminate different enantiomers. So this functional micro robot is has propulsion by hydrogen peroxide, and the quantum dots on the surface can allows to see the motion of this micro robot also. In the middle way, it can be sensing different kind of enantiomers. I want to show you a video of the supporting information from this paper, in which it's working. Yes, you can see here how is the motion of this micro robot. It's like a rocket, and it's interesting for people who never saw this kind of nano robots or micro robots, and the new application is very interesting also. With yeah, you can see here the motion with different concentration of iron peroxide. It's a very new way to for sensing. Moving to a project from my group, I'm currently working in a new sensor using also quantum dots. For that, I'm using magnetic nanoparticles, which is decorated by quantum dots on the surface. And after the incorporation of beta cyclohydrin, the string, which is like a molecule which can discriminate analytes depending of the size of these analytes. We can make a sensor for imidazole, for example. In acid media, the steric impediment avoid the imidazole to go inside of the beta cyclone stream. However, in basic pH is the opposite way. The imidazole can go inside of the cyclostring, and we can check the differences in order to know what is the quantity of this kind of analyte. This is a real image of a nanoparticle, magnetic nanoparticle decorated with quantum dots. I don't know if you can see here the small balls is around the whole surface of the quantum dots. It's only a representation, but the real situation is full of quantum dots here. It's a very good image. So moving for switching applications, here the strategy is almost the same. For example, in this case, there is no electronic transfer, but they are using the quantum dots in a multilayer with a polymer, which after the reduction or using potential or lower potential, they can change the absorbance of this polymer. These absorbance correspond to the wavelength emission of the quantum dot, and you can see here how the intensity of the fluorescence is changing, going to zero. There is not here electronic transfer between the quantum dot and the polymer, but it's a very interesting way to see a switch. Here in this case, 6 electron transfer from the quantum dot to the polymer. Here there is a polymer with a quantum dot, and after the application of higher potential, the oxide polymer. There is a electron transfer from the quantum dot to the oxidized polymer, and after the reduction, this electron transfer disappeared. So we can get again or recover again the fluorescence, resulting in a switch. Here is by many cycles for this kind of samples, and you can see here how it's so stable, and with a very good switch. Another sample is from this paper, which authors made a multi-layer surface containing quantum dots and fluorescing by covalent bonding, and after the oxidation, they were expecting to get a reduction of the fluorescence or quenching due to the electronic transfer from the quantum dot to the fluorescent. And in the reducted fluorescent, they will have to recover again the fluorescence. So as you can see here, there is an on-off situation by reduction or oxidation, and there is a switch also here, and also a good switch, not very stable, but it's good also. Following this strategy, in my group, we are trying to develop a new surface for switching applications using quantum dots attached to a silane on a conductive surface, which is Ito, with fluorescing attaching on the surface of the quantum dots. In our case, we don't want to use multi-layer, just a monolayer. And we hope after the reduction, observe an increasing effect of the fluorescence, and after the oxidation, a decreasing effect. It's a on-off situation. For that, we made fabricate and then a device, which probably many of you know this infrared setup for solution samples, for liquid samples, sorry. And we modified this setup in order to use a surface with electrochemistry inside for optical measurements. It's a front view of this device, and this is the conductive surface containing this the quantum dots and the sample. And after the reduction, we observe on-off situation. Reduction, with a reduction, we have an on situation, and with oxidation on off. And this is the switch we found. We use as a reference only the quantum dot without the fluorescing, and as you can see here, the switch is so small. However, when we incorporate the fluorescing, this switch has a very important increasing here, due to the effect of the electron transfer from the quantum dot to the fluorescent. So this was a very good result, and we are about to publish it. And to finish the samples, I want to show you an example in a real life. Samsung, the business, the company, the firm, are using quantum dots for their TVs. This is a difference between OLED TV with a QLED TV, which is an acronym of quantum dot LED. And I want to show you a part of the advertisement in which they explain more or less how they can increase the color or the wavelength emission using quantum dots in order to get a better color, better stability in the image, and to improve the effect of this screen. And if you move for the side, for example, you also can see perfectly the effect. And so I want to say this speech is sponsored side by Samsung. It's just a real sample I wanted to show you. And as a final conclusions, we can conclude that the quantum dots they have a very straightforward fabrication. They are very stable thanks to the ligands or other kind of ligands with a very easy functionalization. The fluorescence is very known how to control it, so it's another advantage of the use of this kind of nanoparticles, and they have a very wide range of applications. And I want to show you here a figure containing some some applications or other applications that I commented because there are a lot of them. But many of them are used for sensing, biosensing, bioimaging, or any other way which you need a fluorescence or any other emission from a photon emission, or also they used for solar cells, for example, transistor. There are many applications of these nanoparticles. With that, I want to thank you your attention. I hope you have enjoyed the presentation. I wanted to do a very easy presentation, for a better and for a good understanding. Thank you so much for your attention.
Thank you, Angel, for your very interesting presentation. And of course, thank you for accepting my invitation. Now it's the time for questions. So as always, you can write them in the chat and I'll read them for you, or you can open your camera and ask. So don't be shy. Well,
I can. I have a question. Thank you for your seminar. Very clear and very interesting. A lot of examples, very different. I had a curiosity on which is the main factor, the most difficult factor to control in quantum dot fabrication. You showed us size, defects, crystallinity, and so on. Which is the most difficult to control, and which is the most important, the one that determines that affects most of the quantum dot properties.
The most important property to be controlled is probably the size, because if you don't get a good, a very small size, probably you will not get any effect that I commented before about the quantum confinement. I don't know if I can show you here the sample. So yes, here in the size, yeah. Here, if you in a moment you're increasing your size, you lost the quantum confinement. So the most important property probably is this one. Also, the rest of the properties can affect the fluorescence, the emission. But if you don't have very small size, probably you will not get any photoluminescence, and the use of the quantum dot for sensing applications or their use, it isn't necessary, because you are losing the main effect of this nanoparticle. So ligands also affect. I think size is the most important one. The next most important one is the ligand, because if you cannot avoid the aggregation, at the end you are getting a higher material, so you probably can lose also the effect of the quantum confinement. So I don't know if I.
Yes, size is also the most difficult to control, because or it's easy to control a quantum dot size.
Sorry?
Size is the most difficult parameter to control in quantum dot fabrication.
Yes. It's a size, but there are many ways to control this size. There are many strategies for the fabrication with solvent salts and other factors. But yes, the size is very important. Thank you.
Okay, we have questions in the chat. The first from Oriana Newman. Are there any other industrial applications other than the Samsung TV?
Yeah, there are applications for not for sensing. It's for example, cells, solar cells, because it can improve the electron injection after the excitation by a light. And I don't know if there is another one which it can be used for no sensing or for no determination of something, but probably will be something, but I don't know any other.
Okay, and the other one from Elena Allegritti. She say, thank you for your very nice presentation. And what about quantum dot stability? Do they tend to aggregate?
The stability of the quantum dot is very good. However, is very determined by the ligand. The ligand has an important role about that. And if you have a good ligand with I don't know, the length, for example, of the ligand, of a ligand which it hasn't any interaction or any electron transfer from the quantum dot to that to this ligand, is in general is very good, and you will not have any problem. Sometimes if you want to do quantum dots in one pot, for example, for decorate some molecules or some nanoparticles or some other materials, you will have a problem. For example, in the case I presented before here, so second. Okay. In my research here, we do this this quantum dots in one pot with a magnetic nanoparticle, and sometimes we have a problem because they can generate different structures or different bondings, or in general it's going well, but you can get other possibilities to get another materials or another structure which you don't want to get. So in general, if you do separately, it's very good, but the stability. But if you want to make a one pot fabrication, sometimes you could get no desired structures.
Okay. So, are there more questions? Well, waiting for more questions, I have a couple of curiosities too.
Mm-hmm.
So the first is related to my work. I work with in preparation of liposomes and nanovesicles in general. And so do you think that it's possible to combine quantum dots with these systems?
I think it's possible, depending what you want to find or what are you looking for. But yes, you can, for example, I don't know, if you are working with vesicles, probably you are working with his effect or to containing some drugs. Maybe you can use this quantum dots to get inside of the vesicle in order to know the kinetic of the drug from the outside getting inside, or who is the effect of the drug inside the vesicle or around the vesicle. Also, if you want to decorate this kind of vesicle. I don't know. I think there are many applications for quantum dots. So, but I didn't see any research which they try to do something like this. But I think it's very, very interesting.
Okay, thank you. And the other curiosity was about the toxicity of these materials. So I was thinking about using them to label biological material or in vivo or in vitro. And about that, do you think that it's possible, or some of them are toxic, or what do you think about that?
Yeah, there are many research about the toxicity. I don't really know everything about that because I don't work with in vivo cells or experiments, but I know quantum dots are toxic depending on the amount of these nanoparticles. For avoiding this effect, there is another kind of quantum dot, which is a carbon quantum dot, which can be used in a real cell or in a real organism without this toxicity, which has this kind of semiconductors. So I know is that they are toxic, but there are options to avoid it. Also, the ligand in some cases are used. If I remember, and then in this for this purpose, I think there are many options to avoid this toxicity.
Okay, thank you. And about well, in this broad range of application, what about the costs? Are quantum dots expensive to prepare or not?
No, they are so cheap. You only need a combination of salts. You can buy them commercially if you want, but they are so cheap. I recommend to you, depending on your experiments or your purpose, if you want to do something special in which you want to incorporate quantum dots, for example, in vesicles, probably it's better do it yourself. But if you buy them, they work very well. So depends of the purpose. It's better buy them or fabricate them.
Okay, so thank you. And are there more questions or curiosities? No. So if there are any questions, thank you again, Angel, for your presentation.
Thank you to the organizers for inviting me.
Of course. And we can move on. I would like to just introduce the seminar of next week. The title will be Through the Looking Glass and What Alice Found There, Chirality in Science and Technology, presented by Professor Andrea Marini. And so thank you for joining today, and see you next Thursday.
Thank you. Goodbye.